Dr. Solani's asked me to talk about biomass life cycle assessment and future trends. And I'm going to do a quick little review here. I work for NC State University and the University of Washington, so I have an interesting perspective because I have my hat in both camps, Western Forestry and Southern Forestry at the same time. So I'm going to do a quick introduction, give a little bit of an introduction on some specifics of life cycle analysis so we know what we're talking about. And then tomorrow there'll be some other talks that talk more in depth about life cycle analysis and actually show components of it. I'm going to be talking more in general, and I think the last talk today will also mention life cycle analysis. I'm going to give a little bit of a history of LCA, where it came from. I keep saying life cycle analysis, it's really life cycle assessment. Then talk about how LCA has been used in forestry and how that's changed over the last 20 years, and then give just some insights and things that we've learned out of the LCA and LCA-like analyses that we've been doing in forestry, and then some future directions, applications, and some conclusions. So basically a lot of the LCA stuff was focused looking at carbon and carbon issues, global warming, energy, etc. And so forest carbon exists basically in 4 pools: the forest. It exists in the products that are currently in use, and that may be durable wood products, energy products, fuel products, etc. And it also exists in products that are landfilled or recycled, and then just energy. The assessment of carbon in this whole area needs to look at all the pools. If you only look at one pool, you'll end up with an analysis that'll produce incentives that may go the wrong way and may hurt various different industries. So life cycle assessment, in general, the goal is to compare the full range of environmental effects assignable to products and services. It has 4 basic phases: the goal and scope, the life cycle inventory, that's where you do all the accounting work, and that's where a lot of the detail and the difficult aspects are. How do you estimate this? How do you account that? And it's a lot of detail from the birth of a product all the way through the entire life cycle. The impact assessment is basically you do multiple inventories and compare them to each other. Now you have a differential analysis, that's the assessment part of it. And then the last phase is the interpretation. Basically what we're trying to do is quantify this. Now we have to remember that that carbon or energy exists in a bunch of pools, which includes our products and energy that comes from our forests. If you're only looking at one of the pools, you don't always get a good result from the analysis. So you always have to be looking at the multiple pools. So LCA actually, initial concerns basically showed up with Newton's law of thermodynamics. We started thinking about energy and where energy was and where it got converted to, and the fact that we never lose energy, we just may not be going where we want it to be. And so at that point we started thinking about energy, things like carbon, and that was really the genesis of where the ideas of LCA came from. Post-World War II, this led to many new energy forms, and we wanted to know what's better, nuclear versus this, versus that, versus coal. And so the investigation started evolving. In the 60s, it introduced the first resource environmental profile analysis, or these REPAs. And that was actually Coca-Cola Company looking at packaging. Should we use aluminum cans versus glass bottles, or this new technology called plastic? And they wanted to know which was going to be better financially and environmentally for their business model. That's really where a lot of this stuff came from. In the 70s, there was a book that came out called Limits to Growth, and people were starting to be concerned about waste and things like that. But then in the later 70s, the energy crisis happened and everyone started focusing on energy. That refocused the efforts back to energy instead of waste. But really in the 70s, it was the waste concern first, wise use of resources, and then it went to energy. In the 80s, we developed multiple criteria, systematic approaches. We basically were codifying the process of how you go about doing this, how do you account for things, instead of people just making up numbers, basically. And it systematically was applied to appliances, automobiles, and housing, and you'll notice the housing there, this is where forestry got linked in, because that's durable wood products and other products that were used. In the 90s, the term life cycle assessment was codified as that's the official term. You'll see analysis assessment used, but it's really assessment. The LCA stands for assessment. It grew into a body of systematic, inclusive, analytical approaches. In the 90s was the advent of the first international standards on how you do the processes, and that's the ISO standards. There's a newer ISO standard than that now, but that's the initial one. 2002, the UN began adopting LCAs, and we just continue to evolve them, and they're becoming more and more interested and used in various industries. Now, from the scope question, there are all these different scopes, cradle to grave. That's a full life cycle analysis. That's from raw materials all the way to the end of life of the product. So that's all stages of processing. And so in the context of forestry, that's you plant a seedling, you fertilize it, that has to include production of the fertilizer. A real full one, which we never do in forestry, would also include the production of the equipment used to plant the seedling, etc. We usually don't ever do that. That's a separate analysis. There's also cradle to gate. That's basically raw mineral extraction all the way to the product is produced and on the loading dock to ship to a customer. So that's not a complete analysis to the end of life of the product, but that's a complete through all the production cycles. There's cradle to cradle. There's gate to gate. There's well to wheel, which is basically the transportation fuels analyses, and Jesse will talk about that tomorrow. And there's economic input-output life cycle analysis is where we're trying to actually bring in financial concerns, because all of the first ones were not involved with finances. It was just whether it's economical or not. It was just purely, is this a good thing from a pollution or carbon or energy standpoint? And then now emerging is some new ecologically based LCA, which are trying to take into account other environmental concerns, other pollution concerns that weren't included initially. So the life cycle inventory and then the resulting assessment needs to track carbon and energy, and I'm equating those two basically as the same thing here, and other chemicals across every state of processing. And so if that involves a raw material, that's mining or refining the raw material, and that gets included, built up to product. So a lot of the classic LCAs you see are for like a toaster. And so what does it take to produce the plastic that goes into a toaster? What does it take to produce the metals? How much? And then how do you assign all the environmental impacts to all of those components, construct it, and then be able to assess the products? The nice thing is once you do that, now you can actually start looking at, well, what if we used an alternative in the construction of this thing, this product? Does that improve or make our environmental footprint worse? So we have the ability and tools to start assessing that. LCI, LCA is the method for doing this that's evolved. There are ISO international standards. The principles are now accepted by IPCC, so all of the climate concerns around the world, LCA is part of that now. The EPA now emphasizes LCIs and LCAs. So if you're involved in U.S. environmental regulations associated with the EPA, you will likely have to address issues related to LCI at a minimum and possibly LCAs. And Helene mentioned earlier the Energy and Independent Security Act in 2007. This codified the requirement for LCAs for the advanced biofuels. If you want to do and produce those advanced biofuels, you need to be doing LCI and LCA work to prove that you're improving the carbon footprint. So in forestry, basically LCAs started with just packaging. It was a like paper product packaging. It quickly went into housing, manufacturing processes, has evolved into forest production. We're now actually looking at LCAs of growing all the trees and what does it take to produce this crop versus that crop. You'll see some of that tomorrow. Went into durable wood products. This was building residential building products, has expanded into other building products, has evolved into the energy products, and again Jesse will show you some of those now, and also is being applied to business practices at this point. So in forestry back in the 80s, the Consortium for Research on Renewable Industrial Materials was formed, and there's a number of people in this room that have done work and research for Quorum over the years. I'm one of the ones that has done some of the forest production side aspects of it. But this is a consortium of 15 research organizations with the goal of understanding the environmental burdens for every stage of processing and product use. And the original focus was on two production areas, the Pacific Northwest and the Southeast, of producing wood in forests, and two residential buildings, basically houses, in a cold climate that was Minnesota and a warm climate that was Atlanta, Georgia. And then looking at the complete environmental assessment of if you built those houses with wood 2x4s versus the alternative. In Minnesota, that's steel 2x4, and in Georgia, it's cinder block. What are the environmental footprints of those differential constructions? So the LCAs have now been done with production from 4 regions of the country: Pacific Northwest, Inland West, Northeast, North Central, and Southeast. And those 2 houses are done, and now biofuels and alternative energy LCAs have been completed also. So basically that's all the detail of this, where we've got production, we produce logs, we produce products out of it, we build houses or use it for energy use, and we're just trying to track everything that goes in and out to see what the environmental burdens and footprints are. This is a schematic from one of the LCA textbooks just showing the different processing stages of a bioenergy system versus a fossil reference system, or using your fossil fuels, natural gas, coal, etc. And it shows that there are some different processing steps in here. They need to be accounted for on both sides to do a fair comparison. This is just to highlight that different engineered wood products have different environmental footprints. Resin energy, these are the glues that are put into engineered products. OSB has a lot. Dried lumber or green lumber has none of that. And so depending on what product you're talking about, the components that go into the LCA, what you're constructing up for your final end product, all of these details matter. This is just a slightly different view where we're actually looking at the differences between using different construction methodologies. So instead of looking at one product versus another, now we're looking at wall studs versus floor, and if we use wood or steel or something else, what are the greenhouse gas or global warming potential associated with those different products? So we can do all these calculations and begin to look and analyze how we want to do construction in the future. So LCAs exist for durable wood products from multiple regions of the country and for multiple engineered products. They also exist for alternative bioenergy and biofuels pathways. And a lot of these results are codified and now put into the US LCI database. If they're not in there already, they're in the process of being incorporated. And that database is housed by or maintained by the National Renewable Energy Lab. And it is one of the better sources of information that can be used with the LCA software to put together, if I want to produce this kind of wood product in this region of the country, what's the alternative electrical grid source, etc. It allows you to do these LCAs by getting all this information into the LCA, US LCI database. Now there are European equivalents, etc. A lot of the LCI concepts are actually coming out of international literature, European literature, but this is the body of the work that's been constructed in the United States. Now we'll go on to some of the things we've learned where people have been looking at these issues in forestry for probably over 20 years now. The location of production matters. You saw a little bit of that in some of James's slides and even Helene's earlier. This is just comparing the carbon in the forest for a Pacific Northwest forest versus a Southeast forest. So if what you wanted to do is maximize the most carbon standing on an acre, you probably don't want to do it in the Southeast. But this doesn't ask the question of how fast, how many acres are there, etc. This is only one part of the puzzle, but location matters. An acre in different places is going to produce a different amount of biomass, therefore carbon if you want to sequester it, or energy if you want to use it for energy. We need to know that information. How you manage the forest matters. The same acre, this is mixed, actually 293 plots in Missouri, managed one way produces this amount of carbon, managed a different way produces that amount of carbon. So basically the same kind of forest being managed different ways can produce significantly different amounts of biomass, therefore have significantly different amounts of energy available or sequestration potential. So how you manage matters. To highlight that a little bit more, this is a theoretical acre in the Pacific Northwest. If you don't harvest at all, you just leave it alone, that line is the no management, what's being accumulated in the forest. If you do harvest it, these lines below, the green is what's standing in the forest, so you have significantly less carbon in the forest. But if you count the carbon in the products, and if you count displacement, and if you count substitution, and I'll talk about those in a little bit, and if you can take advantage of bioenergy, you can get above the carbon that would be standing in the forest if that forest was standing there. So if you can look at some of these other advantages that we can have by using our renewable resources, we can be ahead from a carbon standpoint and or an energy standpoint. Now, a lot of these analyses of how much biomass or carbon is available are actually founded on top of biomass relationships, and the way you calculate biomass or estimate biomass is critical. This is just showing the stems, 5 different equations for Douglas fir in the Pacific Northwest. You have a fairly large range of what the equations say the biomass is. The real answer is cut it down, burn it, and find out what the energy content was. We can't do that for 100,000 acres. So we're relying on a series of equations, and if we pick an equation that we know is high, we may be overestimating. If we pick one that we know is low, we might be underestimating. So what we really need to do is run it through multiple equations so we have some kind of sensitivity. So we have some variance associated with our estimates, and we're not terribly good at that. Soil carbon versus forest carbon. Soil carbon may be equal to 3 times the amount of carbon that's in the above ground system. Now, if what we do on top of the ground doesn't affect what's under, it doesn't matter. But there's increasing evidence that what we do on top changes what the soil carbon is. And if we're looking, if our concern is global warming, greenhouse gases, by managing forests, there is the potential that we would release this larger below ground pool. That may be a concern. There's a lot of research that's beginning to look at that. There's some evidence that there are some systems that are relatively well buffered. If you're managing above in a sustainable manner, the below ground carbon is fine. It's not being released. In other systems, that's not the case. You do almost anything above ground, you start releasing carbon out of the soil. And if that's that significant compared to the forests that we have, that may be something that we're pumping into the atmosphere, a considerable amount of carbon. So that may be a concern. How you look at things also matters. In this case, what I'm highlighting is if I look at a single stand, this is the carbon profile of a single stand managed through time. You have a lot of carbon, you harvest it, there's a lot of dead material, it grows back. This is the stem, branches, and foliage, and then dead litter. And so if you see this pattern, it's probably analysis looking at a single stand or a very limited number of stands. but you do not harvest every stand on a landscape at the same time. So the real answer is this is what's happening with the carbon in the forest or across the landscape. So if you're doing this to a small number or small percentage of the area, which is what we actually do in forestry because we have to wait 40, 50 years, 20 to 50 years to get an end product, this is what we should be analyzing, not this, over a broad scale. So it matters how you look at things. And there have been some analyses in the past that didn't realize that. Disturbance is important. This is simulated carbon yield in the future in western forests. The bottom graph is with wildfire. If we don't deal with wildfire issues in the West, nature may release the carbon for us. And there's a lot of policies out there that are encouraging us not to harvest forests in the West. And if they do burn up, a lot of that greenhouse gas is not released as carbon dioxide. It comes off as methane, which is a lot worse than carbon dioxide. So it has the potential of a huge impact on carbon in the atmosphere if that's a concern. Now, I mentioned earlier the concept of displacement. This yellow is displacement. Displacement is where you're using the energy of the waste wood, and we're actually really good at this in forestry already, for process energy. So instead of running the machines in a mill off of the electrical grid, be that coal, natural gas, whatever, we're actually using the wood waste within the mill to power the plant. And there are many plants now that are at or getting very, very close to a net zero energy balance where they can run the entire operation just on waste of producing their products. That's this displacement. That's the amount of carbon and energy that we did not have to pull off the grid because we're using a renewable resource that sequesters carbon. That can be significant. The blue is landfills. We're also doing analyses where we're tracking after a house has been used for 80 years, it's dismantled. Some of that wood's immediately recycled. Some of it ends up in landfills. We actually track the carbon in the landfill also as part of the analysis. So that's displacement. The next concept is substitution, and that's this gray area, which is a huge number, you notice. Again, this is the carbon in the forest, the stems, branches, leaves. These are products here. These are shorter term products, landfill, and then the top line is substitution. Substitution is if houses are going to be built, if you build them out of wood versus if you build them out of steel. So this gray area is if the house was built out of steel, that uses so much more energy to produce that we're actually giving ourselves credit here for not having to spend the energy to build the house because we made it out of wood instead. And that displacement factor may be equal or greater than all the other carbon we're talking about in a relatively short period of time. Now, we've been talking about these concepts for a number of years. That concept is not accepted internationally in the greenhouse gas and global climate reductions, but it's beginning to gain some traction. We call this the biomass bucket or the forest biomass bucket. Just because the biomass is in the bucket doesn't mean you can use it. There's the issue of there is biomass out there, and some of the studies that we've seen have said there's X million tons of biomass and it's all available. Not true. Some of it's already spoken for. Some of it you couldn't collect it off the acre at any price. And some of it should stay because we need that for resource protection, site quality, habitat, etc. So that biomass, we're actually only talking about some fraction of that, and that fraction is different in different kinds of forests and in different parts of the state and in different states and different parts of the country. So we need to get better estimates of what those rates really are of what could be biomass and what is available, what's really available. And then just to show some pictures instead of all the graphs, this is actually a biomass harvesting operation in eastern Washington, where they're effectively loading all the sticks in the back of dump trucks and hauling it off to a co-fire facility, I believe. Competition for supply exists. You heard James talk about this a little bit. This is out of the Washington Biomass study. Some facilities are very sensitive to price. Some facilities are not sensitive to price. That matters where they're located, how many competitors they have, what feedstocks they're feeding off of. Why this matters so much is these sensitive to price, you put one more mill, that might drive other facilities out of business because they're too sensitive to price. So we need to know and understand that. If we want to export pellets to Europe, will that affect the pulp industry in North Carolina, yes or no? And if so, is that something we actually want to do? Maybe we do. Maybe paper is more efficient coming from somewhere else and we shouldn't be in the business of paper. But we need to make decisions on that, because if we don't, we're actually making the decisions anyhow. There are unintended consequences of policies instead. James talked about distance. This is a feedstock area for eastern Washington, and the same kind of jaggy edges because of roads, mountains, rivers, things you can't get across easily, significantly change the shape and distribution of those. Little things like oceans. You know, for pellets, you want your facilities near a port to ship them to Europe, but that cuts half your feedstock area out. Makes transportation a bigger issue. So transportation really does matter, and what I've seen in the South and in the West, much more than 30 to 50 miles, you can't afford to haul the little stuff that's being targeted for energy products at all. So if you have to go farther than that, you probably can't do it financially unless someone's willing to pay you a premium for it. Price for feedstock matters. In this case, it's Washington, and this is a given facility, not really revealing the name, but at different prices per ton, that's how far they can afford to go to pay for biomass. So if they're getting paid by Europe a premium, they can go collect stuff a far longer distance. In my opinion, and not everyone agrees with this, but in my opinion, bioenergy, either for fuel or for heat, is going to be in association with other forestry production. Except in some cases there will be dedicated energy crops on more limited acres that may go straight to transportation, fuels, etc. But if it's the woody biomass, it's probably going to be in association in some way with more traditional forestry. And so these analyses are looking at, if you build 2x4s and build houses, we can add this much more if we go to cellulosic ethanol from the wood. If we get better conversion processes, cheaper enzymes, whatever conversion pathway you're using, that number will go up a little bit, but that's an increment, not the whole ball of wax, basically. And then here, this is just highlighting that according to this analysis, the fuels doesn't give you as much of an increase as going to cogen or direct burning. But there are very good reasons to want to produce fuel instead of just pure energy. The pure energy might be more efficient, but fuel's got this other little issue of independence from importing oil. And that may be a more valuable thing than just pure energy production. Another alternative that's looking at ethanol from willow compared to putting 2x4s in houses. So you may get better carbon sequestered from the house, but there may be other considerations why you want to go a different direction. This begins to give us the tools to go, what are the magnitude differences and what do we want to pay for any of those differences, financially or socially. One last one here. This is a base case without ethanol here. There's actually a better bump in ethanol because of the feedstock being used for the analysis. And then here we're actually taking everything that would have gone into paper and we're using that as energy instead. So we can do all these kind of differential analyses and start looking at the different industry segments and begin to decide what the impacts are going to be on some of our incentives. So the bottom line of all of this is that different products are going to have different mixes and impacts, amounts of energy available, and carbon impacts. We need to know that, we need to quantify that, and LCA is giving us the tools to produce these numbers so that we can begin comparing things. So some lessons learned, additional lessons learned. Higher fossil fuel or carbon prices will allow us to pay to collect forest residuals and waste. It'll pay us to go farther than we otherwise could. That means we can have larger facilities in a given location. But that requires those prices to be higher. It would pay us to use more wood in construction, so substitute back for steel or other alternative building materials. Use wood siding instead of vinyl siding. Use wood sashes in windows instead of vinyl. There's many opportunities for wood products that are very, very good versus some of the alternatives that have shown up. But for that to work, we really need either higher energy costs or higher carbon costs. That would also allow us to use more biofuels but not have to steal feedstocks from other existing uses of those wood. In other words, stealing it from your small diameter operations, engineered wood products, or paper. And that's one of the concerns as we ramp up to produce all these energy projects. What's that going to do to other segments of the industry? Now this is actually, I've stolen this slide from Jesse there. I don't know if he's going to use it in his presentation tomorrow, but I'm just wanted to point out these are all the feedstocks that were analyzed in this paper that Jesse's been working on. And here's natural gas. So those are all clustering at a very similar level for price. Now the left, this is lower greenhouse gas impacts versus higher greenhouse gas impacts. And Europe has decided they want to be over here. So they're buying pellets for fuel. They've made that decision. They're willing to pay. Purely from an economical standpoint, you'd want to burn coal because that's the cheapest per BTU. If the cost of natural gas doubled, biomass is in the catbird seat. Investment will flow into all kinds of energy facilities. They'll get built and we'll be in a great situation. But if natural gas price goes in half, which happened a couple years ago, you see a lot of that investment in development dry up. So we are actually very sensitive to the cost of alternatives from a fuel standpoint. Now that still doesn't mean that's not a direction we should go from a policy standpoint, because there are other reasons we might want to go there. A little bit on policy and incentives. We need to understand the carbon and energy from a life cycle perspective across linked carbon pools. We can't just look at one pool. And a highlight, and if we do look at only one pool at a time, you tend to get counterproductive incentives. And as an example, I'm going to pick on corn ethanol. That's a subsidy that exists. CCX was trading carbon at $2 per ton. Europe's got it at 13, and that subsidy works out to be $295 a ton for carbon. Just so that we can have ethanol from corn to drive in our cars. We're overpaying per ton of carbon. Now that was done, or that resulted because we only looked at one pool of carbon. We didn't look at how everything's related. And that's a danger when we don't look at a broad analysis. So be careful what you ask for. In many cases, that's not terribly a good thing to have asked for. So incentives to remove forest residuals to increase biofuels can be productive. But not if the incentives divert wood feedstock from higher valued uses. And if the best use of carbon is sequestering in houses, that's what we should be doing. If the best use is for fuels, that's what we should be doing. And we need the tools to be able to analyze it to figure out what the best uses are. And then as a society, we need to decide what that best use is. Incentives for the biofuel end product will bid feedstock away from other uses. That's a concern. Will energy products from forests kill the pulp industry? Yes or no? There's a lot of noise about that. That's one of the reasons you haven't seen some of the timber companies jump on the bandwagon for biomass, because they're growing this and they're cutting off that because they're an integrated company. That's where their concerns come from. Cap and trade is actually often counterproductive. Cap reduces oil demand, prices adjust to the floor, so now we have a commodity that's at a minimum price instead of a higher bid price. And then the trade compensates rule makers, certifiers, lawyers, not the resource producer or the consumer. So cap and trade, even though that's what's being used around the world, it has some problems associated with it also. A few more details. This is out of looking at global warming potential out of a spreadsheet from BioGrace. This is used in Europe for a lot of the LCA and LCA-like analyses, and I was involved in some analysis of production of forestry and sending pellets to Europe in an energy plant, looking at the global warming potential and greenhouse gas impacts of that. So the chemical you're interested in actually is critical. If you're producing carbon dioxide, that has a global warming potential of 1. If it's methane, it's 23, which actually has been up to 28 now. 28 times larger impact for global warming than CO2. So what does a forest fire release to the atmosphere? A combination of carbon dioxide and methane. And the bad one down here is actually N2O, which is from your fertilizers, nitrogen fertilizers. Turns out to be a hot spot for production, because if you're concerned about the global warming impacts, that number is 296 times worse than carbon. So you have to be careful about what chemicals you're producing in your production processes. Here I just want to highlight different fuels. The top ones are natural gas, diesel, gasoline, methane, ethylene. All have different carbon impacts, grams of CO2 per megajoule associated with them. We figured this out. We can compare different energy sources or fuel sources to figure out which ones are better or worse. This is all embedded in the LCA, LCI work. And then this is just an abbreviation of one of the analyses that I did. Here we're producing softwood in the southeast, and these are the grams of carbon equivalent per megajoules of pellets that are going to be shipped to Europe. This is how much carbon has to be billed to this production process, basically. This is the harvesting, this is chipping, this is hauling it to the pellet plant in the U.S., this is the producing the pellets, this is getting it to the port. So we've got a pellet mill that's so many miles away from the port, haul it to the port, put it on a ship and go 5,765 miles on a ship to Europe, and then get it to an energy facility and then burn it finally. So all the stages, and you can see that yes, that transportation to Europe, that's a pretty big number, but not all that big compared to making the pellets in the first place. And these are the kinds of calculations Europe is needing to do to prove that if they buy the pellets in the U.S., they're actually decreasing their carbon footprint. So they're tracking these things. So substitution has the highest leverage and potential if all we want to do is sequester carbon. But that's not the only thing that we want to do with our forests. But energy has a more direct impact on energy independence. Now, it doesn't need to be an either or. We probably need some mix of both. But we have to figure out what that mix is going to be. Policies and economic incentives change the situation. Just 2 weeks ago, House bill in the state to repeal the RPS for North Carolina. So that would have gotten rid of a lot of the incentives for renewable energy in the state of North Carolina. Pushed to end it, it died in committee. It's okay, it's not going to be repealed, but it'll come back. Don't worry. A lot of people are looking at these issues, and I'm just trying to highlight here that our situation or the environment that we're doing these analyses in will change. And it may change just because of an RPS for a given state. So renewable energy standards, I'll just comment, might actually be counterproductive to efficient use of our forest resources. Depends how they're put together. New policies, economic incentives, and economic development projects change the situation. This is Wilmington Port. They're putting storage facilities in now. They got it under the radar. They are going to export pellets. They're increasing their ability to store. They're moving that direction. No matter what's going on with the RPS, no matter what's going on anywhere else, they're convinced that pellets are going to go out of that port. They're tooling up. Once they're tooled up, that influences the landscape because now it's easier and cheaper to export. So a lot of little things are going on that change the situation. New technologies and innovation. Fracking's being debated. North Carolina was supposed to write some rules. That's been held right now. There's a question on what the lobbying pressures are, but the fracking rules in North Carolina are currently held up. That may change the natural gas price. And it's not just North Carolina, it's all the fracking rules that are coming online in all the states around us too. Now, North Carolina doesn't have a whole lot of that resource, but there is some. But there's a lot of interest in making that available or not. And then complete new technologies. Who knows that right now, this week, an all-solar airplane is flying across the United States. It's going to fly from California to somewhere on the East Coast and not use a single fossil energy. What's the units I want to talk about here? It's all solar. There's new stuff coming online all the time that might change the picture. That might be conversion technology. That might be a completely different energy source we hadn't thought of before. It's all changing. We need to make sure any incentives positively impact the total across the energy pools. Now that may mean that some product is going to go away because the greater good is for paper to be produced somewhere else and us to make fuels here. We may want to reallocate things. So there may be segments of the industry that will be very upset. Store carbon in the forest or pump it into products? That's an easy question. Which do we want to do? Incentives can help with that. And let me back up. Prevent unnatural wildfire by thinning in the west or burn it up and put it in the atmosphere. We can make decisions on that. And LCA gives us a tool to help us evaluate those alternatives. So the units may change. We used to talk about board feet, then we talked about cubic feet, now we're talking about tons. It's very likely in the future we'll be talking about energy equivalent or global warming potential as a currency that we're buying and selling our products with. LCA is increasingly written into requests for proposals for research. I don't know how many of the RFPs we've seen over the last couple years, but almost every one of them is getting LCA, or at least LCI written into it. You got to do this stuff. So it's something that is definitely growing. It's a growth industry because of environmental concerns. Universities are tooling up on curriculum to teach LCA. NC State's one of them. It's improving our capacity to educate people so that they can do it and do it credibly. The EU crisis has not reduced their demand for renewable energy. You would think with countries going bankrupt, if anything was going to make them not keep chasing their new energy policies, that would do it, and it didn't. Things are changing around a little bit, but they're still committed. They're decided. And so that didn't change it. Soil carbon may come to haunt us. Regional differences are important. We've seen a little bit of this. Just because it's one way in North Carolina doesn't mean it's going to be the same in West Virginia. We need to be able to do these analyses and build the LCA capacity. Using wood displaces fossil emissions. It should target the most fossil-intensive products and fuels. Just because we can build product A that competes with product Z doesn't mean that's what we should do. We might actually should be looking at product X because it's a bigger impact and we can get farther if we compete against it instead. So we might actually need to do product development targeting various industries. LCAs need to be done as new feedstock alternatives are developed. You've got a new genetic variety. If it's different enough, we need to know, we need to do additional LCAs. And the methodologies will evolve through time. As an example of that is the new evolution of LCA. There's a new concept called dynamic life cycle analysis. This is basically looking at the fact that your energy grid is not static. That energy mix is changing all the time. And so we need to actually incorporate that into our LCAs because previously we just assumed that all the same energy was always available. Well, that's not true anymore, so it's evolving to try to incorporate some of that. So opportunities exist to steer the trend of product design. And this is mostly stated from engineering of buildings. Quorum's worked very heavily with architects trying to get wood more used in commercial buildings. There's a huge potential there for wood in commercial buildings instead of steel. And so my last slide, the pessimist in me thinks it's too complex. Society will never be able to make an informed decision and make the right decision. But the optimist me says, we've got all these tools. We've got a lot of information and data. We just need to use them and educate ourselves to make informed environmental decisions and wise decisions about the uses of our resources. Thank you.
Questions?
In one of your slides, I think, had a red bullet in it that said renewable energy standards may be counterproductive.
Yep. If you make an RPS for North Carolina that produces incentives for transportation fuels, that may not be the best use of the wood from the forest. The best use might be build houses.
From an LCA perspective, then you're saying, or just
From a policy, what we should be doing, and what LCA does is gives us some tools to be able to compare those so that if they aren't equal to each other or one's not better, we're actually making an informed policy decision of why we want to go a way that might not be the most efficient use of the energy from the forest. And there are very good reasons why we would want to go that direction, but we ought to be making that decision as an informed decision instead of having some incentive that was a simple to adopt compromise in some committee that decides, oh, well, we favor fuels over houses or houses over fuels, or cogeneration over fuels. We just need to be aware of what those decisions will do, and in some cases, the incentives will push the wrong direction and may damage an industry that we want to preserve.
I see the LCA being really with things like sentiment. John Carrick, the Ash friend of mine, and Anderson is passionate about the fact they consider the fact that we ought to be using the forest resources to remove energy efficient systems out there. European style systems that are 90% or better. Well, do everything per joule. Compare that to a 30-some% power plant, and then the LCA ought to inform that
Yes.
issue.
Yes.
On the other hand, you look at some issue like what we're dealing with now. Our next client is one of our biggest poultry industries in the state, who is having a hard time getting food savings required for their turkey houses and chicken houses, because the savings are now being reported.
Right.
And how an LCA helps that, that's subjective impacts type things you referred to earlier.
Yeah, in theory, the LCA could help with that, but it's an issue of how you develop the scope of the analysis. And the more far-thinking or future-thinking people are making analyses that includes wood shavings for poultry industry compared to wood products or fuels. You can do that. You can do the LCI of those different uses of the resources, and then LCA gives you the ability to compare them. Now, there are some economic-based LCA that are being developed. What's more common to be done is you do the LCA and a financial analysis that's coupled to it. There's some evolution of LCA that tries to include all of that in the LCA process. Right now, that's not very mature, and so most people are kind of doing them coupled to each other. I think that's a lot of what Jesse did is they're both being run on identical analyses, so that you get both, in other words. Go ahead, Steve.
Jim, if I might just add to
Oh, please do.
I think the coupling all that in one analysis is so full of assumptions.
Yes.
I see that as, frankly, pretty
Yeah.
but to say, all right, here is a series of carbon alternatives.
Yep.
For your
All the LCIs, right.
Well, there's a lot more than carbon, than just the effect.
Mhm.
There's a lot of attributes other than carbon. Frankly, probably matter as much.
Or more.
But then this fact that somebody can't get the material they want at a price, in a sense, the LCA, that's not its problem. It's simply saying, here are carbon flows. Where this gets iffy is if you're using that LCI to incentivizing pathway 1 versus pathway 2 for some greater good.
Right.
And the LCI then tells you, right, is that greater good 10% or 100%?
Right.
And you get you get high resolution data.
Can be really
tough. So
it's hard enough getting the data to do an LCI in the first place. And then when you start doing some of this comparative stuff. So what I think, to kind of restate what Steve says, you do all these LCIs. Where it makes sense, you do the LCA that compares the production and use aspects of it. But you remember the 4 phases, there's the scope, that's important. You do the LCI, you do the LCA, and then there's interpretation. Well, this is interpretation and beyond that Steve's talking about. That's not the end of the use of the information. That's got to go into policy development and incentive development of decisions on the LCI information that's using us to inform the policy and incentives. And so that's kind of in the interpretation and beyond. is where all of that comes. And we're not terribly good at that. We're really good at going, oh, well, this fixes that problem, and then, oh shoot, it created 12 others, the unintended consequences. Being able to think through what those are before we create those consequences instead of just throwing Band-Aids on every bad thing that crops up, that's what we need to get a lot better at. And if we can figure that out, these are the tools to help us do that and try to make those informed decisions. So, thank you.
Thank you.